Hello everyone, I'm Francesco Percassi and welcome to this talk. In this talk, I will discuss how can we formulate a relevant scheduling problem, that is the quality of service aware approximate real-time tasks execution on multiprocessor systems, into a planning task by using a high-level planning formalism, that is PDDL+. As a convention, in the following, I will shorten the name of the considered problem into QoS-Aware TMS. Historically, planning and scheduling were considered separate branches of computer science, addressing different problems. Planning concerns on identifying what actions to carry out in order to achieve a goal, whereas scheduling concerns determining when and how to perform actions to optimize a metric criterion. However, in real-world applications, this distinction becomes more blurred, and in some cases, planning and scheduling are integrated together. In this work, we aim to reformulate a QoS-Aware TMS problem into a planning task to enable the use of the large number of techniques developed for automated planning. The context in which we can find this scheduling problem is the context of approximate computing-based real-time embedded systems. In these kind of systems, the outcome depends on the correctness of the results and on the time allotted for the computation. In such critical systems, we prefer to get approximated results achieved in a timely fashion instead of more accurate results obtained after the deadline. These applications are typically organized as a set of tasks represented by means of a directed acyclic graph, namely the precedence task graph, PTG, which imposes an ordering on the task's execution. A PTG is a DAG in which T is the set of tasks, and each edge represents a precedence relationship involving two tasks. Given a task Ti, we can define the primitive which returns all the preceding tasks of Ti. In G, there is a unique final task that we call the sync node, and the most important aspect of this problem is that each task has a mandatory part, denoted with M, and an optional part, denoted with O. Furthermore, each task has k different versions, each of them associated to the execution of a portion of the optional part. So now we can formalize a QoS-Aware TMS task as a triple in which G is a PTG. Nu is the number of available resources, which are the processors on which the tasks are executed, and delta, that is the deadline. Our objective then is to find a schedule that executes all the tasks within the deadline, using at the same time at most new resources, by choosing the versions of each task which maximizes the overall quality of service. And the quality of service is equal to the sum of the selected optional part length for each task. In this picture, there is depicted a graphical representation of the considered problem. On the left side, we have a PTG having 6 tasks, in which the task T2 has 3 variants. On the right side, there is a possible schedule over 2 processors compatible with G. The planning community developed several planning formalism, and in this study we choose as a target language one of the most expressive. PDDL Plus is a planning formalism for describing dynamic systems in which there is a discrete and a continuous component. The core aspect of PDDL Plus is the possibility of modeling the agent and environment. A PDDL Plus task is a tuple pi in which f and x are the sets of propositional and numeric variables. I and g are the initial and goal state, and A is the set of actions. Finally, E and P are the sets of events and processes, and they are used to model the environmental changes outside the control of the agent. Processes are constructs used to model the exogenous and continuous changes that affect numeric variables when time passes. To be specific, when the precondition of a process holds and time passes continuously, then the numeric variables affected by the process change over time according to a set of ordinary differential equations described by the continuous numeric effect of the process. In this work, we use a very restricted class of processes just for handling the linear flow of time, as provided by the process raw time. Events are similar to processes, but changes, instead of lasting over time, are instantaneous, and they can affect both propositional and numeric variables. As soon the precondition of an event is triggered, then the state of the world changes instantaneously according to a set of numeric and propositional assignments. In this slide, I reported the overview of the presented reformulation from A to pi. In pi, the propositional variable f are used to synchronize the execution of the tasks and to keep track of the executed and running tasks. The numeric variable x are used for the global and local timers, one for each task, and for the number of occupied resources. In the initial state, all the timer and the occupied resources are set to 0. The goal G requires that the sync node has been executed and the deadline is satisfied. In pi, we have an action for each version and for each task of G. Finally, E and P are used to model the temporal execution of the tasks. The execution of the tasks is modeled with the triplet action process event, using the notion of the start-stop model provided by PDDL+. The action associated with the J version of TI task can be executed if TI has not been executed, all the source tasks preceding TI have been executed, TI is not currently running, and there is at least a free resource to use. The execution of this action causes the occupation of a resource, and secondly, the activation of the process raw TI, which keeps track of how much time has passed since the resource was occupied, and the execution of TI is started. After a quantity of time equal to Lij is passed, where Lij is the sum of the mandatory part Mi and the selected optional part Oj, the event associated with the J version of Ti is triggered. This causes the deactivation of the raw I process, the release of the occupied resource, and the completion of the task. In this figure, we have a graphical representation of the start-stop model. Given a task Ti, we have k actions and events, a pair for each version, and one process. For executing a version of the task Ti, we have to select the corresponding action. This execution activates the process used for simulating the temporal execution of Ti, enables the J event, and occupies a resource. When the process has been executed for a time equal to Mi plus Oj, the previously enabled event is triggered, causing the block of the process, the release of the resource, and then the completion of the task. For concluding, in this preliminary work, we have reformulated a relevant scheduling problem into a PDDL+ problem. Unfortunately, in PDDL+, the use of custom metric has not been studied in depth as in other planning formalism. Therefore, our model cannot be used by PDDL+ planning systems, taking in consideration the quality of service. This problem could be overcome by designing ad hoc PDDL+ heuristics that are sensitive to the quality of service. Alternatively, we could use other target languages such as PDDL 2.1, which allows the use of custom metrics. Using the original formulation of the scheduling problem, in which all the temporal lengths are natural numbers, even classical planning could be used. As future work, we would like to reformulate this problem in simpler formalism using this first step as a reference for future translations. So, thank you for your attention.